in the last lecture, we were discussing plane groups formed by the hexagonal two-dimensional lattice. So, this is where we were. So, here we have a primitive hexagonal lattice to which I have added the point group 3 m. So, there are two possibilities for this point group to be added to the hexagonal lattice. So, one possibility is we put these mirror planes along the cell edges. So, one mirror plane is out here, let me kind of out here, which is along the cell edge, another one out here, and there is a third mirror plane which is along the shorter diagonal of the cell. So, this is one possibility, and this is what we had done in the last lecture. Just let me just repeat that last bit of that lecture. So, let us consider the mirror plane, and let me call this as M1, the one on the short diagonal. Now, what would happen if I did a reflection operation sigma 1 across mirror 1, followed by the lattice translation. So, I have lattice translation, two of the lattice translations are A bar and B bar along the two edges. So, followed by A bar. Now, this translation is at an angle. So, we probably expect that there would be a glide plane somewhere. Now, what do we do to figure the glide plane? We have to break this translation into two components, the parallel component and the perpendicular component. So, the parallel component would be parallel to the mirror. So, this I will call it as T parallel, and a perpendicular component would be like this. So, that is T perpendicular. So, what I have done? I have put A bar as two components, T parallel plus T perpendicular. Now, one thing to note is that the T parallel, the magnitude of T parallel is exactly half of the lattice translation along that direction, because the lattice translation would be going from one corner of the cell to the other corner, and we are at midway. So, therefore, the result of this combination of reflection and translation should result in a glide sigma tau, where tau is the glide translation, which would be equal to T parallel, and we have already seen that this is exactly half the lattice translation. Hence, this is definitely a glide plane. And what is its location? We have also seen that in the earlier lectures. Its location is at exactly half the distance along the perpendicular component, and as a result we expect. So, suppose this is my midpoint of the perpendicular component, I will get a glide like this. Let me call this as G1. This is the glide plane 1. Now, consider another situation where I take the reflection operation sigma 1 again, follow it up. So, let us not take the mirror plane 1 now, let us take a different mirror. Let us take this as the mirror now along one of the edges. So, that my reflection operation is sigma 2, follow it up with the lattice translation A. Again, I can divide the vector A into two components, T parallel, which in this case turns out to be the same as before, and a perpendicular component to mirror 2. No, in this case that will not work. This is the wrong thing I have taken, that I am dealing with mirror 2 and not mirror 1. So, my parallel component I will take up till midpoint. This is T parallel, let me call it as T parallel prime, and the perpendicular component will end up at the lattice point. And therefore, there is another mistake I have done in this case. I am not taking the vector A, but rather I am taking the diagonal translation from one corner to the other corner, and let us call that as t as the vector t. Therefore, I do a reflection operation sigma 2, follow it up with t, and we want to look at what is the result. The result would be another glide plane sigma tau. Again, this tau would be equal to the magnitude of the parallel component and located at t perpendicular upon 2. So, let us see where this glide would come. So, my perpendicular component is this one, hence I will get a glide cutting through the midpoint of the perpendicular component, and I get this glide G 2. And in fact, that is all I need to do in this particular problem. All other glides will appear as a result of the symmetry operations, the other symmetry operations. And in fact, if you think about it, I will get a glide like this as well, I will get a glide like this as well, and those are all the glide planes that I will get. So, let us just look at the final result. The final result is this. This result occurs when mirrors are placed along the cell edges. Now, consider another orientation of this point group 3M, another orientation of the mirrors in this group. So, in the first case we have mirrors along the cell edges. Now, we have mirrors perpendicular to the cell edge, as you can see in this figure. Let me remove this clutter a bit. So, now let us consider this. Where are, so I will just also remove these equations, so that I can write a fresh set of equations here. Let us take one of the perpendicular mirrors, let us take this, let us call this as mirror M1. Now, let us look at a particular operation, reflection operation sigma 1 across mirror 1, follow it up with the translation vector A. So, my translation vectors are A and B here. Now, let us look at this vector A. This vector A can be broken up into two components. The parallel component is along the mirror. So, this is my parallel component, and the perpendicular component is along one of the cell edges, T perpendicular. Very clearly, I do not need to do anything more. The glide plane should appear at the midpoint of this perpendicular component and parallel to the mirror M1, which means that this is how this mirror would be. Now, is T parallel exactly half the translation vector in the particular direction or not? Let us look at this diagram. Let us draw two adjacent hexagonal cells. My T parallel component is this, but it does not end at a lattice point. If I extend this further, it will end up at this lattice point. So, it starts with a lattice point of one corner of one cell, ends up at a lattice point in the adjacent unit cell corner. And you can see clearly again that T parallel is exactly half the lattice translation which joins one lattice point to another lattice point. Hence, this is my, if I call this, let us call this as glide G1. So, I have here sigma tau, where tau is obviously T parallel located at half the perpendicular component. Consider the reflection operation sigma 1 once more and follow it up with this time the translation along the short diagonal. Translation along the short diagonal, let me call that as vector T. Now, what I will have? I have my parallel component, which is the same as in the previous case along the mirror, and my perpendicular component comes out here, let me call that as T perpendicular prime, which is just the opposite of T perpendicular, and hence the glide plane now would be parallel to the mirror at midpoint of the perpendicular component, and hence I will get a glide plane in this manner. Now, consider the situation where my mirror plane is along the long body diagonal. So, I consider the operations of this, I should complete this sigma 1 followed by T, this thing gives me another glide. Now, sigma 2 followed by, let us see the translation vector B, and we again look at where are my components. So, this is my translation vector B, which I again break up into a parallel component T parallel prime and the perpendicular component, call it as T perpendicular double prime, and let me call this as T parallel double prime as well. And very clearly I do not have to explain, my glide plane will show up parallel to mirror 2 in this fashion. I think now by symmetry we will be able to replicate all the glide planes that are there, and therefore, I will just erase this figure to remove the clutter and show how the complete set of symmetries in the cell will look like. So, as you can see that this was my glide G 1, and if I call this as glide G 3 and call this as glide G 2, this is my glide G 2 and this is my glide G 3, and all other glides by other symmetry operations would fall in place. So, here now we have two plane groups based on the primitive hexagonal lattice and the point group 3 m by simply changing the orientation. Now, no other orientation would be possible in this case. So, these are the only two plane groups that we will see. Now, there is a predicament of how do we give the notation. Earlier we were simply adding a primitive in case of primitive or centered in the case of centered lattice, and we would simply put the point group. But here that would mean that it should be P 3 m, but then it will become the same notation for both. So, in order to distinguish between the two plane groups, our notations in this case is called P 3 1 m and P 3 m 1. Now, I think this needs a bit of an explanation that what is the logic behind giving these two notations. So, let us very briefly look at it. It is very simple. Some of the plane groups you would have seen that there are some shorter notations, in some cases they become longer, but there is a general notation which can be and which is also sometimes called as a long form of the notation, which can be applied to every plane group that we have seen. Now, that notation is based on that it will have 4 symbols. So, I will just look at it in this manner, that I have 4 symbols for a notation. So, let me just put these 4 dashes. So, this we are talking about notation. The first symbol in the case of plane group will be either a lowercase p or a lowercase c. P stands for primitive cell, C stands for the centered cell. So, whenever you see a cell whenever you see a notation which starts with a C, then very clearly we are going to talk about only centered rectangular lattice. So, in fact, we are talking about a rectangular lattice. If P, then it would be one of the other primitive lattices, which one can understand by seeing the rest of the symbols. The second symbol we will put as the highest rotation symmetry. The third symbol will choose a symmetry perpendicular to x axis, or we can simply call it as a axis. And the fourth symbol would be symmetry at an angle alpha to again the x axis or the a axis, whichever way you want to refer. So, let us now look at this P31M and P3M1. So, first of all, P stands for primitive. Highest rotation symmetry is the threefold rotational symmetry. So, that is the second symbol that follows. Then I have 1 in the top figure. 1 stands for, this is a third symbol, a symmetry perpendicular to the x axis or the a axis. Well, in this case, we do not have any, in fact, the second and third symbol will always be either a glide plane or a mirror plane. So, the symmetry would be, there is no symmetry, there is no glide plane, no mirror plane perpendicular to in fact any of the axes. So, therefore, which basically means it is a one fold symmetry or no symmetry. So, the third symbol becomes 1. The last one is again could be a mirror plane or a glide plane, it would be at an angle alpha. So, I have put M there. Now, M obviously the mirrors are at some angle alpha, it could be 0 degrees, it could be 90 degrees, it could be 60 degrees or 45 degrees. So, that is how we get the symbol P31M. Let us look at now the second plane group P3M1. Again P3 is clear, primitive, threefold rotational symmetry that we will put as the second symbol. Now, it says third symbol is mirror M, and third symbol we have already seen here, symmetry perpendicular to the x axis. So, in this case the orientation of the point group was such that the mirrors are perpendicular to both in fact the x and the y axis. So, mirror will go as the third symbol, and there is no other symmetry to put on the fourth symbol. So, it becomes P3M1. So, we have these two plane groups done. We have still not looked at one plane, we have taken care of all the point groups so far out of those 10 groups. We have not looked at 6 mm. We can put 6 mm added to the primitive hexagonal lattice. Now, this is an interesting one. I have put all the mirrors of the point group 6 mm into this diagram, and you can see that we have the rotational 6-fold axes at the corners, and we have also have the 2-fold rotational symmetries in the center of the edges and the center of the cell. If you want to know how these symmetries came about, the 2-fold symmetries, you can go back to the lecture where I had discussed adding a 6-fold or point group 6 to the hexagonal cell. And of course, we also have the 2 3-folds inside the cell which are at the centroids of the 2 equilateral triangles. Now, looking at this, I am sure there are going to be a lot of glide planes, but actually it turns out to be quite simple because we have already done 2 plane groups P3M1 and P31M, and let us look at them again. Let us just look at the placement of the mirrors. In P31M, the mirrors were put along the cell edges. In P3M1, the mirrors were put perpendicular to the cell edges. In the case of 6 mm, we have mirrors, we have a lot more mirrors, and there are mirrors along the cell edges, parallel to the cell edges, and we have mirrors perpendicular to the cell edges as well. So, it essentially if I just take the plane group P31M and P3M1 and just superpose on this diagram of P6 plane group, I will get all the exactly the same mirrors, but superposed, both of them superposed of the two plane groups P3 1M and P3M1. And therefore, logically the glide planes will also get superposed on the diagram, and so therefore, I put all the glide planes as well, and we form the plane group P6MM. You see, there is a lot of symmetry in this diagram. There are lots of mirrors, lots of glide planes which form the plane group P6MM, and once we put motifs in this, those motifs are also going to move around, basically forming a very interesting and a very intricate pattern. So far, if I count all the plane groups that I have done, if I add up all the plane groups that I have done in the last couple of lectures, including this lecture, I will find that I have done so far 13 plane groups. But the question is this all? Well, I have exhausted all the point groups. I have added all the point groups to the 5 lattices in all possible manner. So, therefore, at first glance it may appear that should be end, and that should be all the 13 plane groups that are there. But there is something else also we can do. So, there are a few more possibilities, and let us discuss those possibilities in the next lecture. I will close this lecture. We will begin the next lecture by considering all the possibilities and then coming out with the entire set of plane groups. Thank you.